the first unit to kind of break.
Okay, somebody had questions on the assignment? Jackson?
I had a question about 10B.
Well, let's start with number 10 in general, okay? Do not make number 10 difficult. So, you have two different masses, okay? Right? And the first thing you want to find is the weight. Now remember, in physics class, physics has this very specific definition of weight. It is not pounds, it is not kilograms, it is only measured in newtons. So basically, you're trying to figure out what's the downward force of attraction between this mass and this rock that we're on, okay? And it's a simple calculation. You just take mg, okay? Take the mass, whatever it is, multiply it by 9.8 meters per second squared, okay? So this goes back to even graph number 1, okay? So graph number 1 should look something like this, where you have mass here, and you have force here, and it's going to go something like this. So there's a couple different ways that you can view this slope. This is going to be relevant back to number 10. So if you come over 1 kilogram, you go up 9.8 newtons. So one way that you can view this, and might be helpful in today's lesson on net forces, that the slope of this line, one option that you could do is 9.80 newtons per kilogram. Okay, that's what the slope represents. So the gravitational force that's applied is 9.8 newtons per kilogram. So if you have 2 kilograms, hey, that's 19.6. If you have a half a kilogram, it's half of that is 4.9. So today we're going to spend a lot of time talking about the gravity mafia and the frictional mafia. So this is also the rate at which the gravity mafia charges you to get something up in the air. The gravity mafia charges you $9.80 newtons per kilogram of something that you want to lift up. So if I happen to have, say for example, a 1 kilogram mass, which I do, so if I want to lift that up, the gravity mafia says, hey, we're going to charge you $9.80 per kilogram. Now, if you're a purist, and you're like, oh, Bergkamp, let's look at the units. Okay. That's 9 newtons, right? Which are kilograms meters per second squared. And if you divide that by kilograms, the kilograms cancel out, and you get 9.8 meters per second squared. So the other way that you can view the line is that the slope represents the acceleration caused by gravity. So you can either view it as newtons per kilogram, or the slope of the line is meters per second squared. So when you get to number 10, and it asks for, hey, which one has more inertia? So one of the things, my purpose on number 10 is a couple of things. Number 1 is that you realize that mass is proportional to force in terms of gravitational force. So the more mass something has, the greater gravitational force is that acts on it. But you have to have more force acting on it. So if I take Hank the bowling ball and this tennis ball, and I drop them, there is much, much, much more force acting on Hank than there is on the tennis ball. But Hank also has a lot more stuff. So since Hank has so much more stuff inside, it takes more force to get Hank to move with the same acceleration as the tennis ball. So one of the things I want you to get out of your minds right now is the idea that, oh, gravity is the same for everything. For God's sakes, no, okay? It's not. Does it produce the same acceleration? Yes, but the gravitational force is not the same. It's not. If the gravitational force was the same on everything, we'd just pick a number and call it 10, okay? What does everything weigh? 10. No, it doesn't, okay? The more mass an object has, the more gravitational force there is on it, but you end up with the same acceleration. So this is why on number 1, why the slope of this line is the same, because it represents your gravitational acceleration. But what it shows is that the more mass that you have, the more force there is acting on it. Okay? So when you get to 10C and ask, hey, we're gonna drop these things. Once you drop them, what's the only force acting on them? Gravity. So your answer to 10C is just the same as your answer to 10A, because once you drop it, that's the only force acting on them, is the weight of the object. Okay, so do not make 10C complicated. And then D, the acceleration, well, I can guarantee you, if you take that weight, 3.92 newtons, and you divide that by the mass, what's that mass, 0.4, whatever it is, okay, kilograms, you're gonna get 9.8 meters per second squared. And if you take that other force and divide it by its mass, you're still gonna get 9.8 meters per second squared, okay? Did that answer that? Okay, on number 5, let's talk about number 5. So on number 5, what are the two most important words at the beginning of number 5? Two most important words. Constant velocity. So what does that mean all the forces add up to?
0.
0. So visualize this. You're pushing this block along at a constant velocity. What are the four forces acting on the block?
Gravity, normal, friction applied.
Yeah, you got your gravitational force, got your normal force, got your force applied, got your force friction, okay? So the applied force is what you're paying to the frictional mafia, okay? So if you can find out what your frictional force is, you know how much you have to pay the frictional mafia, okay? Now, I've given you the coefficient of friction, okay, which is 0.38. That is not the force friction, okay? Don't look at that and go, oh, that's my frictional force, 0.38. If it was actually a frictional force, what units would I put on the end of it? Newtons. Do you see newtons on the end of it? No. Do you know why?
Yes, it's not.
It's not a force, okay? If I wanted it to be the force, I would say, this is the force. That's mu. But you need to find the force friction. So you know that mu times force normal equals force friction, which begs the next question, well, how do we find force normal? Well, there's a handy-dandy little equation that says force normal equals Fg cosine theta. You have to worry about the cosine theta part of this. Not right now, you will, but just not right now. So you don't have to worry about that part, and then you go, but how do we find Fg? Well, if you look, there's another equation that says Fg equals mg. So you can rewrite this as mu times mg equals force friction. So, because if your answer to 5A is wrong, everything is going to be wrong. Your answer to 5A should be very close to your current age. Okay? Very close to your current age. Now, here's what's going to happen. You're pushing this thing along at a constant velocity, 5 meters per second. And then you stop pushing. As soon as you stop pushing, what's it going to do?
Accelerate to rest.
It's going to accelerate because now you don't have all the forces that are in equilibrium. So the frictional mafia, basically, Big Tony comes up to you and says, good boy, right? You're not paying us, we're going to shut you down. So the frictional mafia is going to shut you down. Frictional mafia is, you don't pay us, you're not doing business. You are not going to keep moving forward. So if you look at a force diagram, you lose that applied force. Now, do not confuse inertia with a force. Does this object, this block, whatever it is, does it want to keep moving? Absolutely. It has inertia. It wants to maintain that state of motion. But once you stop pushing it, there is no force acting in that forward direction. So does it want to keep moving? Yes, but inertia is not a force. Okay? Listen to me very carefully. Inertia is not a force. It's an intrinsic property of anything that has mass. So the only reason that that block stops is because there's an unbalanced frictional force. The frictional mafia is charging you whatever you want to do. So when you get to E, because if you understand E, it makes D a little bit simpler. So you're going to draw a velocity time graph. So for the first 6 seconds, what's your velocity?
5 meters a second.
That's just going to be a horizontal line, right? 5 meters per second. So, Olivia, what's the acceleration during the first 6 seconds? Do not make this difficult.
Bruh, it's a
5
trick
meters a
question.
second.
Trick question.
0?
Beautiful. Why?
Because it's at a constant.
Yeah. So your acceleration is going to equal 0 meters per second squared. Now, if you look at that big bad sign that says that force equals mass times acceleration. So if your acceleration is equal to 0, what's your force?
0.
0. Okay? So the net force, and the net force, this is what we're going to talk about today. Your net force is the sum of all the forces. So are there forces acting on the block? Absolutely. But what do they all add up to?
0.
0. Now, at that point, you stop pushing the block. Olivia, then is it going to accelerate?
Yes, it will.
What's the line going to do?
It's gonna like increase.
Bro. Good job.
It's going to go like this.
Yeah. I don't even know what.
Olivia, prove.
Hey, call Jeff, bro.
I don't think so.
So you're going to tell me that I stop pushing it and it speeds up. That's what you just told me.
The line is gonna go. It's gonna decrease.
Slope towards 0? Then let's go with that. I know it's Monday. Okay? Maybe that action? Right? So what's the sign of my acceleration? Positive or negative? Because I'm slowing down with positive velocity. So this is going to have some negative acceleration, which is your answer to number or letter C. Okay? So on C, to find that acceleration, you're going to use F equals ma. So your answer to C would make it GPA. Okay? Not horrible, not stellar, but a fairly decent GPA. Okay? Especially if it was a non-weighted GPA. It might be positive, it might be negative, that's for you to figure out. But if you look at the graph, what has to be the sign of the acceleration? Negative. Because now the unbalanced force is your answer to A, that's about 18 newtons. You know what the mass is, take the unbalanced force of friction, divide that by the mass, so is your acceleration. Now, you want to figure out the total distance that it's going to travel, which is this answer to D. So, at a minimum, you're traveling 5 meters per second for 6 seconds. How far are you going to travel in the first 6 seconds?
About 30 meters.
30 meters. Constant velocity. You can use distance equals velocity times time. So at a minimum, your distance has to be 30 meters. Okay? But now you need to figure out the distance that it's going to take when it slows down. Do not use the 6 seconds. That is not the time it's going to take for it to slow down. The 6 seconds is how long it was traveling at a constant velocity. But let's think this through. What do you know the initial velocity of the block? 5. According to Olivia Pruitt, the final velocity is going to be? What's the final velocity of the block?
Should be 0.
0.
0. You know your acceleration because you just found that on C. Okay? You don't know time. So what are you going to use?
C equals B C2.
That equation. So your overall answer on 5D should be in the low to mid 30s. Okay? Low to mid 30s. All right. All of your answers on 6, 7, and 8 should start with a 1. Actually, 9 as well. 6, 7, 8, and 9 all start with a 1. 6, 7, and 8 are all 10 to the third.
That's fine.
And 9 should be something times 10 to the fifth. Okay? So on 7, 8, and 9, you have to find the acceleration, then multiply that by the mass. Some of your answers, dare I say, might even be a negative value. Okay? On number 2, how many significant digits did I give you in every answer, in every value on number 2? 3. How many significant digits should all of your answers have?
3.
If you, let's just say hypothetically, you have that first answer as 4 meters per second squared. Why is that bad?
1 second.
It only has one significant digit, okay? Because if you look at 4, you're gonna, wow, man, your physics teacher gave you crappy data. I did not. I gave you good data, okay? Don't roll me under the bus and, oh, Mr. Brookhamp gave us bad data. Bull, did not. On number 4, okay? So let me kind of give you a visual on number 4. So this is a hydrogen-filled balloon. We'll deal with that later. So here's a binder clip, okay? Set it down. The forces are in equilibrium. Got the weight of the binder clip pulling down, the block is pushing up, right? Now, I attach the hydrogen-filled balloon to it, okay? So what's, hold on, I gotta recalibrate. Okay? So now with that hydrogen-filled balloon pulling up, what is, now listen to me very carefully. I attach the hydrogen-filled balloon. What has that done to the weight of the binder clip?
Decreased.
The weight itself has to.
The weight of the binder clip has not changed, because it's still the same amount of stuff times G, okay? But what happens to the force that the block has to provide? More or less than what it did before? Less, because now the balloon is providing some upward force. So there isn't as much force that the block has to provide. Now, what does everything add up to at this point? 0, because is anything accelerating? No, okay? Since nothing's accelerating, I know all the forces still have to add up to 0. Now, here's what I want you to see when you draw your diagram on 4D. You should have 3 forces. One of them is acting down, which is your gravitational force. The force in the balloon obviously is acting up. And then the scale is also providing some up and upward force. So on your diagram on 4D, you should have 2 upward forces and 1 downward force. But they all should add up to 0. So obviously, at least one force has to be a negative value. Okay? Because if not, you can't make 3 positive numbers add up equal to 0. Okay. On the question on number 4 about the plane, okay? So, Natalie, come up here. You were just on the plane. Yeah. Sit in the chair. Okay. So, here's the plane. We're going to set the plane. So, you have mass, right? So, therefore, do you want to accelerate?
Yeah.
Nope.
Oh, no, I don't.
You don't want to accelerate.
Okay.
Okay? You don't want to accelerate because you have mass. Newton's first law of motion. Whatever state of motion you're in,
Oh, okay.
that's what you want to stay in, right? Okay. Now, I'm going to push this forward, right? So imagine this is the plane seat. So what do you feel when I push it?
Force.
Which way?
Forward.
Okay? So the tendency is to say, I'm being pushed back into the chair. If that were true, then it would have to be some invisible force field that you can't see, emanating a force that's pushing you back into your seat. Seem reasonable? No.
Oh, no.
Horrible. Yeah, jet lag, I forget. There's no magic force field pushing against you, pushing you back into your seat. What do you want to do?
Stay there.
Yeah, so the chair provides a force forward. Now, what's Newton's third law? Equal and opposite. So when the chair pushes you forward, by Newton's third law, what do?
Go backwards.
You push back on the chair. Now, we won't do this because we like that, right? But imagine that her head was like on the frictionless surface. Okay? It's not, but let's just say. So if I did this and pushed her quickly, what would her head do?
Fall off.
Yeah, it would just stay there and her body would accelerate out from underneath it. Okay? We won't do that because we like it. It's like, what happened to your head? I don't know. Tough one to explain to talk about. So, here is the story. And listen to me very carefully. It's important. When you feel like you're being pushed back into the chair, you're not. Okay? You just want to remain at rest. Now, you can reverse this. Let's say we're going, now I'm going to keep you going. Okay, then I'm going to stop you. Okay, now, when I stopped her, was there a force pushing her forward?
No.
No. What happened?
Chair just been back.
No. What, you kind of went like this, right? Did I push you, but did I actually push you forward?
No.
What did you do?
Opposite reaction.
Well, you kept going because of inertia, right? Because once she got going, she doesn't want to stop. Now, let's say that's the magic frictionless chair, okay? That's the magic frictionless chair, and I stopped the chair, what would you do?
Fly away.
Yeah, you just keep going forward because there would be nothing to impede that motion. Okay? Got it? Good? Thank you. Go down. Okay. Any other questions on the assignment? Going once? Going twice? So get those hands. All right. Marta, stop down the camera for a second.